One of the defining features of a fluid is that when a fluid, a gas or liquid, exerts a force, it is in the form of a pressure. The pressure is the force applied to an area. So pressure is the force in newtons divided by the area in square meters. The standard unit of pressure is the Pascal, and it is 1 Newton per square meter. If you want to know the force applied by a fluid, you would multiply the pressure times the area that the pressure is applied, and that will then give you the force. You should notice that the area over which a force is applied can change the effect that it has. Our video here shows a deck of cards that's getting cut by a blade, and the cards are cut cleanly in half. In the other case, the force is applied evenly over the entire card, and after no effect to start with, eventually, as the force gets much more massive than that of the blade, then the cards are basically just destroyed. The point is that a smaller force over a smaller area may have a much bigger effect than a large force over a larger area. One important example of pressure is atmospheric pressure. The atmospheric pressure is caused by the weight of air that is above us, and the average value is 1.01 times 10 to the 5th newtons per square meter. This can also be called 101 kilopascals. The pressure unit of a bar is sometimes used as well, and a bar is equal to 100 kilopascals, and that's roughly 1 atmosphere. Another common unit of pressure is the pound per square inch, or a psi. Notice in all of these cases, it is a force divided by an area. The force exerted by the atmosphere is something that we are so used to that it's easy to forget that it's around. However, the force exerted on us by the atmosphere pushes on us all the time. One example where it is striking is in an elevated aquarium. This is shown in the picture here, where the air has been removed from the inside of an aquarium and that it's been turned upside down. The result is that the atmospheric pressure pushes the water up into the aquarium, and the fish have a nice view of the pond around them. If there is still air in the aquarium, then that air has the same pressure as the rest of the atmosphere, so there is no effect. You need to remove the air in order to fill the aquarium like this. The atmospheric pressure varies a bit from time to time and place to place. Winds tend to blow from high-pressure regions to low-pressure regions in the atmosphere, with rain and snow usually corresponding to low-pressure regions. Hurricanes and cyclones are examples of extremely low-pressure regions. The pressure also depends on altitude. High-altitude training is sometimes popular because the air pressure and the corresponding oxygen pressure is lower. The percentage of air that is oxygen is still the same, but the total pressure is lower, so less oxygen is available. The idea is that the body adapts to this lower pressure of oxygen by producing more red blood cells, which can then give an advantage for some endurance athletes. Usually the idea is to train for a short period of time before an event to boost this red blood cell count. The pressure varies with the depth of a fluid. Maybe you've noticed that when you dive deep into a pool, sometimes your ear hurts, or if you're in an airplane, your ears pop. The reason for this is that pressure changes depending on the weight of fluid that's above you. That means that the deeper you go in the water, the larger the pressure, because there's a greater mass of water above you. The weight is equal to mass times gravity, and then you can divide it by the area over which the force is applied. The mass is the density times the area times the height. The density is the mass per volume, and the height times area is the volume. That means that the pressure is the density times the height times g times the area divided by the area, or the density times g times height. That means that the more dense the fluid, the more quickly the pressure changes. You'll notice a large difference in altitude has a pretty small shift in pressure, while a few feet of water might be enough to make your ears hurt, because the water is much more dense than air. Notice that this is only the pressure due to the fluid. For example, if you have a pool under atmosphere, the pressure will be the sum of the pressure caused by the depth of the pool plus the atmospheric pressure. Let's say you are 5 meters below the surface of the water. That means that the pressure is 1,000 kilograms per cubic meter times 10 meters per second squared times 5 gives you a 50 kilopascal, which is roughly half an atmosphere. The atmospheric pressure is 1 atmosphere, so the measured pressure at 5 meters deep should be about 1.5 atmospheres. On the other hand, if you remove the air, like a non-vented IV bag, then the pressure only depends on the height. One example of how this works is that the millimeters of mercury is a common measure of pressure. If you evacuate a tube and fill it with mercury, the height of the mercury column would be equal to the pressure applied to the mercury. Because mercury is extremely dense, the height of the column for atmospheric pressure is 760 millimeters, while if you wanted to do something similar with water, the height would be close to 33 feet. Millimeters of mercury, or torr, is another common unit of pressure. Blood pressure, for example, is measured in torr, so the conversion is 1 torr, or 1 millimeter of mercury, is equal to 133 pascals. Okay, so I have some questions coded up for you. These should be pretty straightforward. Watch out on the IV bag question. There's a pop-up question that appears after you've answered the first question, since the second question kind of gives away the answer. Good luck.